Picture a winter so brutal that the horizon disappears in white. The air stings your skin. The wind snarls like a living force. Snowfall doesn't melt for months. Temperatures plunge so low that exposed breath freezes as it leaves your mouth. Now imagine facing this reality with no furnace, no insulated home, no modern gear, only the land itself. How did indigenous communities survive such conditions? The answer is astonishing. They engineered snow into warm, protective tunnel systems that could shield families in temperatures where modern hikers wouldn't last an hour. Most people think of snow as a threat: cold, wet, deadly. But to indigenous peoples across northern North America, snow was raw building material, a natural insulator more powerful than wood, hide, or stone in deep winter. Packed properly, it formed walls that trapped warmth, absorbed sound, and blocked wind so effectively that temperatures inside could rise dozens of degrees above the outside world. Forget the idea of a simple snow cave. These were architectural systems. Tunnels shaped for structural strength, chambers positioned for airflow, entrance pits designed to trap cold air, raised sleeping platforms carved to hold heat, and ventilation ports angled strategically to prevent smoke buildup during cooking. Snow tunnels weren't just shelters, they were survival laboratories created from knowledge passed down over generations. This episode explores the engineering behind them, how snow density determines insulation, why curved shapes prevent collapse, how cold air sinks and warm air rises inside enclosed spaces, and how indigenous families turned one of winter's greatest threats into an ally. If you want to understand real cold weather survival that doesn't rely on modern tools, then stay with this video. And if you're passionate about ancient innovation and practical knowledge that still matters today, hit subscribe and turn on notifications. The cold never defeated them. They learned to build homes inside it. In the far northern regions of North America, winter didn't simply arrive, it ruled. For months at a time, storms erased the horizon, winds sharpened to blades, and temperatures dropped low enough to crack wood. Travel became dangerous, hunting scarce, and daylight fragile. In this world, survival depended on more than endurance. It required a shelter that could defy the cold itself. And remarkably, the solution came from the very force that threatened life: snow. Snow wasn't viewed as an obstacle. It was studied, tested, and understood. Indigenous communities learned that snow, despite its reputation for coldness, holds a secret. Its structure, tiny crystals surrounding trapped air, forms one of the most effective natural insulators on Earth. A thick layer of properly compacted snow can hold warmth better than many modern building materials. When the wind became relentless and temperatures sank to dangerous depths, snow transformed from an enemy into construction material. Where trees snapped and hides stiffened, snow remained workable. It could be cut, shaped, compacted, tunneled, and carved. More importantly, it could protect. Snow tunnels emerged from this understanding. They were built where snowdrifts naturally piled high, where winds sculpted dense layers, and where deep insulation could be shaped with minimal effort. The tunnels didn't rely on external materials or large stores of fuel. They relied on winter itself, not fighting it, but bending it into usefulness. These shelters offered something extraordinary: a stable, quiet, windless environment where temperatures often rose far above the deadly cold outside. Even small fires or body heat could warm the interior, thanks to the insulating power of compacted snow. Winter may have shaped life in the north, but indigenous ingenuity reshaped winter, turning frozen landscapes into habitable worlds. Before a snow tunnel could be built, indigenous builders had to understand snow itself, its density, its strength, its weaknesses, and its hidden abilities. This wasn't guesswork. It was precise knowledge gained over generations of observation and experience. Snow is far more complex than it appears. Fresh snowfall is light and powdery because it contains large air pockets between crystals. This kind of snow is useless for construction. It collapses instantly. But snow that has settled, drifted, or been wind-packed undergoes a transformation. The crystals lock together, compress, and form layers with strength comparable to lightweight stone. This dense snow doesn't melt easily, doesn't shift under pressure, and can be shaped into stable walls that withstand enormous weight. Indigenous builders knew how to read snow. They tested blocks by listening to how they cut. They looked for color changes that indicated compression. They judged stability by the sound of their own footsteps. A single misjudgment could lead to collapse, but a correct choice produced walls capable of holding strong through storms. Inside these tunnels, science and survival merged. Because snow traps air inside its structure, heat produced by people, lamps, or small fires becomes sealed within. The surface melts slightly, refreezes, and forms an icy inner shell that further strengthens the structure. Paradoxically, the interior becomes warmer than the outside world, even though the shelter is made entirely from frozen material. Builders also understood how snow responded to heat. Too much fire caused dripping and weakening. Too little warmth left the interior uncomfortably cold. Ventilation played a crucial role in regulating both temperature and air quality. This mastery of snow wasn't accidental. It was engineering rooted in natural physics, knowledge that turned a frozen landscape into a library of construction materials. Snow wasn't feared, it was harnessed. A snow tunnel wasn't just dug into a drift. It followed a deliberate blueprint that blended engineering intuition with generations of refinement. Every curve, every angle, every chamber had a purpose. Because in minus 40 degrees conditions, even small design flaws could become fatal. Construction began with choosing the right drift or bank. Builders sought snowpacks thick enough for carving, dense enough to hold shape, and positioned away from wind that could erode the structure. Once a suitable site was chosen, the entrance was cut low, intentionally lower than the living space inside. This sunken entrance created a cold trap, allowing frigid air to settle outside the main chamber rather than circulating where people slept. After the entrance, the tunnel gently curved upward into the primary living chamber. This rise was strategic. Warm air naturally moves upward, so lifting the interior above the entry protected precious heat. The chamber itself was rounded. Domed ceilings and curved walls distributed weight evenly, preventing collapse even under heavy snow accumulation. Sleeping platforms were carved along the sides, raised above the ground to avoid the coldest air layers. These platforms were smooth, slightly sloped, and often lined with hides or brush for added insulation. The rounded interior also minimized drip points and helped guide warm air evenly throughout the space. A small ventilation hole was carved at the top of the dome. This was the lifeline of the entire structure. It allowed smoke, moisture, and exhaled breath to escape while preserving the warmth inside. Builders maintained this opening regularly, clearing frost buildup and adjusting size depending on weather. The result was a shelter that balanced insulation, airflow, and structural stability with remarkable precision. A snow tunnel wasn't a crude survival tactic. It was a carefully engineered winter machine designed to keep life safe, warm, and thriving. Inside a snow tunnel, warmth wasn't a luxury. It was a finely managed system. Indigenous builders understood that a shelter carved from frozen material could, counterintuitively, become surprisingly warm. But achieving that warmth required deliberate choices about airflow, fire use, and heat retention. The first principle was simple. Air moves in layers. Cold air sinks. Warm air rises. Builders shaped tunnel interiors to take full advantage of this. The living chamber sat higher than the entrance, creating a natural thermal barrier. The coldest air remained trapped near the entrance pit, while the raised sleeping platforms captured rising heat. Even without a large fire, temperatures inside could climb dramatically thanks to body heat. A handful of people talking, cooking, or simply resting transformed the chamber into a warm pocket, protected from the brutality outside. But warmth had to be managed carefully. Too much heat caused the interior to melt and refreeze into slick, unstable surfaces. Too little made the shelter uncomfortable. Small lamps, fueled by animal fat, were sometimes used for light and modest warmth. These lamps burned cleanly, producing a steady glow and gentle heat without overwhelming the structure. Their flames were low, controlled, and placed strategically to avoid melting the walls. Ventilation was the key to everything. A small opening near the top allowed warm, moisture-heavy air to escape, preventing condensation. If moisture collected inside, it could drip onto bedding, freeze, or compromise the structure's integrity. Builders checked the vent often, adjusting it during storms or clearing it after heavy snowfall. Interior surfaces also played a role. As warmth accumulated, the inner snow melted slightly, forming a thin layer of ice that strengthened the walls and improved insulation. This self-sealing effect made the shelter safer and more efficient the longer it was used. Snow tunnels didn't just trap heat, they managed it, creating stability in a world defined by extremes. At first glance, a snow tunnel's rounded shape seems simple, even intuitive. But behind those curves lies one of the most important engineering principles ever discovered. Arches and domes distribute weight better than any flat surface. Indigenous builders didn't need textbooks or diagrams to understand this. Experience taught them that a curved ceiling could withstand the crushing load of deep snow, violent winds, and shifting ice far better than straight walls. Snow, once compacted, behaves almost like stone. It is strong in compression but weak in tension. A flat roof forces the snow to push downward in a way that creates tension, leading to cracks and collapse. But a dome transforms that downward force into outward pressure, allowing the structure to support enormous weight without breaking. This principle shaped every part of the tunnel. The ceiling was carved into an even arch, smooth and continuous, with no sharp corners where cracks could begin. The walls curved gently inward, guiding stress away from vulnerable points. Even the sleeping platforms were rounded, blending into the walls to maintain structural integrity. The curves also influenced airflow. Warm air collected in the highest part of the dome, helping regulate temperature. Moisture condensed along the walls rather than dripping into the living space. The rounded shape ensured that rising heat moved in a slow, circular current instead of pooling unevenly. Builders recognized when a dome was too thin, too flat, or too sharply carved. They listened for subtle changes in sound when tapping the walls. A hollow echo meant danger. A solid thud meant stability. These instincts were passed down through practice, not instruction manuals. In the harshest conditions on the continent, curved snow structures provided safety, warmth, and remarkable durability. They stood firm through storms that could flatten wooden shelters. The brilliance of these forms wasn't guesswork. It was engineering perfected in ice. Inside a snow tunnel, life slowed into a rhythm shaped by warmth, silence, and careful routine. The world outside could howl with blizzards and punishing winds, but inside, the air was still. The walls softened sound. Light flickered gently. The environment encouraged efficiency and calm, because survival demanded both. The day often began with tending the entrance. Overnight winds could bury the opening, so clearing it was essential. Once the tunnel was open, builders checked the vent hole above the chamber, making sure airflow remained steady. Good ventilation meant everything: fresh air, safe heat, and a dry interior. Cooking was done sparingly and with intention. Small lamps or low flames warmed food without risking collapse. Meals were modest but high in energy, chosen to conserve fuel and maximize heat production. The heat from cooking also contributed to the overall warmth of the chamber, a welcome boost during the coldest stretches. Movement inside the tunnel was deliberate. People avoided brushing heavily against the walls, which helped maintain structural stability. Bedding was kept dry and raised on carved platforms to escape cold air that pooled near the floor. Snow that tracked inside from boots or clothing was quickly brushed out to prevent melting and ice buildup. Despite the confined space, these shelters supported community routines. Families talked, repaired tools, planned hunts, and waited out storms together. The warmth generated by their shared presence created a microclimate drastically different from the freezing world just beyond the entrance. Nighttime required preparation. Lamps were dimmed, bedding adjusted, vent holes checked once more. A single ember or warm stone could provide hours of comfort, allowing people to sleep deeply even while temperatures outside plunged to dangerous lows. Inside a snow tunnel, survival wasn't frantic. It was organized, calm, and supported by careful habits refined across generations. Snow tunnels were not always isolated shelters. In some regions, and during particularly harsh winters, indigenous communities expanded them into interconnected networks, forming pathways beneath the snow that allowed movement, communication, and safety when the surface became impossible to cross. These networks weren't vast urban labyrinths, but carefully planned extensions designed to meet the needs of winter life. Imagine a storm that lasts days, wind speeds high enough to hide landmarks, visibility reduced to nothing. Walking on the open ground in such conditions could mean getting lost just a few steps from home. This is where tunnel networks made all the difference. Short tunnels often connected sleeping chambers to storage areas where food, tools, or gear were kept. Others linked one family shelter to another, creating a protected corridor for sharing resources or checking on relatives. Deep snow insulated these pathways, just as it insulated the homes themselves, providing a calm, wind-free environment where communication remained possible even in the worst weather. Larger communities sometimes built surface-to-shelter transition tunnels, allowing hunters or travelers returning from outside to enter without dragging freezing winds into the main chamber. These transitional spaces acted as buffers, places to remove snow, shake out hides, and gradually warm up before stepping into shared living quarters. Tunnel networks also played a practical defensive role. In regions where predators roamed the winter landscape, staying beneath the snow offered protection. Wolves, bears emerging early from dens, or other threats could be avoided simply by moving unseen beneath the drifts. These systems required constant upkeep. Snow shifts with time, and tunnels needed regular reinforcement. Builders inspected for sagging ceilings, compressing walls, or thinning layers. Maintenance was a shared responsibility. These snow networks weren't just engineering feats. They were lifelines, enabling communities to stay connected, safe, and warm when the outside world turned lethal. A snow tunnel's strength depended not only on the snow itself, but on the precision of the tools used to shape it. Indigenous builders didn't approach construction with improvised sticks or random chunks of wood. They carried specialized tools, crafted from bone, antler, ivory, or wood, each designed to cut, carve, and sculpt dense winter snow with remarkable control. The most iconic of these was the snow knife. Sharpened along one edge and curved slightly to guide smooth cuts, it allowed builders to slice clean blocks from compressed drifts without crumbling the structure. A skilled builder could read the snow with a single stroke, feeling its density, hearing the quality of the cut, and knowing instantly whether it was suitable for carving. Some knives were long and flat, ideal for smoothing interior walls. Others were more compact, used for trimming delicate edges around vents, entrances, or sleeping platforms. Handles were designed for use with mittened hands, ensuring a firm grip in freezing temperatures. Carving was done methodically. Large chunks were removed first to shape the rough interior, followed by fine scraping to smooth surfaces and even out curves. This wasn't cosmetic. Smooth walls strengthened the tunnel and improved airflow. Builders learned to maintain wall thickness by sound alone, tapping gently until the tone signaled whether the snow remained dense or had thinned too much. Tools needed care as well. Blades were wiped clean of ice buildup. Handles were inspected for cracks caused by extreme cold. A damaged tool could compromise the tunnel, so maintenance was as important as construction. Craftsmanship in snow might seem temporary, but during deep winter, it was life itself. Every cut, every angle, every polished surface demonstrated a deep connection between people, tools, and environment. Snow tunnels weren't merely carved. They were crafted with intention and mastery. Inside a snow tunnel, warmth didn't come from a roaring fire. It came from something far more subtle: the heat generated by the human body. Indigenous survival systems relied on this truth. When insulated correctly, even a small group of people can create a microclimate capable of pushing back against deadly cold. A snow tunnel structure made this possible. Its thick, compacted walls sealed in warmth. Its curved shape encouraged even heat distribution. And its elevated sleeping platforms kept people above the coldest air, allowing their combined heat to rise and collect in the upper chamber. In this environment, the warmth from bodies, breath, lamps, and shared activity didn't vanish, it accumulated. Body heat alone could raise interior temperatures dramatically. A tunnel that sat in -40-degree weather outside might hover around freezing or slightly above inside. And with several people, temperatures could rise far higher. Clothing of fur, hide, or layered plant fibers added another level of retention, keeping warmth close to the skin and reducing heat loss into the air. Even breath mattered. Human breath contains heat and moisture, both essential to warming the air inside the chamber. Too much moisture could frost the walls, but controlled airflow managed this naturally. The small vent at the top allowed humid air to escape, while dry, fresh air filtered through the entrance pit. This delicate balance created a stable indoor climate, warm enough for rest, cool enough to maintain structural integrity. Movement contributed too. Preparing food, adjusting bedding, carving snow blocks, and simply shifting positions released small pulses of heat. In a sealed space, nothing was wasted. Every gesture added to the collective warmth. In the end, a snow tunnel was less a shelter built around a fire and more a shelter built around people themselves, transforming human presence into an engine of survival. Snow tunnels were strong, but they weren't maintenance-free. Their safety depended on daily vigilance, a rhythm of checks, adjustments, and quiet discipline that turned a carved shelter into a dependable winter home. In regions where storms could strike with little warning and winds could reshape entire landscapes overnight, this discipline meant survival. Every morning began with inspection. Builders studied the slope of the ceiling, checking for subtle sagging that signaled compaction or weakening. They listened for soft cracks, faint warnings that indicated a shift in the snowpack above. These sounds guided immediate repairs, smoothing, reinforcing, or reshaping interior surfaces before small issues became dangerous. Ventilation was monitored constantly. Frost could choke the vent during the night, blocking airflow. Clearing it restored the delicate balance of warm and cold air inside the chamber. A blocked vent didn't just lead to stuffiness. It allowed moisture to accumulate, which could drip, freeze, or weaken the tunnel's structure. Airflow protected both the people and the architecture. Storms required special preparation. Snow was packed against the outer walls to reinforce insulation, but builders ensured the entrance remained accessible. Markers, sticks, antlers, or carved poles were placed above the entrance so it could be found even after heavy snowfall buried it from view. Inside, bedding was fluffed and dried, stones warmed if heat was needed, and tools kept close at hand. Night brought another round of quiet tasks. People rotated watch duty to ensure the vent stayed open and the entrance didn't seal shut from drifting snow. Even small sounds outside, shifting wind, fresh snowfall, distant cracking, could signal changes that required attention. A snow tunnel was never left to chance. It was a living shelter, strengthened by awareness and maintained with the same care that built it. Survival wasn't luck. It was attention. Patient, practiced, and unbroken.